State-based model of electrical network. Now, how to find the state-based model of electrical network? So, consider a simple RLC series circuit. This is a simple RLC circuit. Now, how to obtain the state-based model of this network means by applying basics law, that is Kirchhoff's law, Ohm's law. Write the network equation, then select the state variable, then finally plot the state-based model. So, how do you choose the state variable means? So, one the concept is that is the number of state. We have to choose the minimum set of state variable. That is the number of state variable is equal to order of the system. Order of the system. This is second order electrical network. So we should take two state variables. Generally, for electrical system, so current through the inductor taken as a one state variable. Then voltage across capacitor taken as another state variable. So now choose current through the inductor I of t. So you have taken as one state variable x1 of t. Then voltage across the capacitor taken as another state variable x2. Okay. Then apart from this, the input voltage EI of t is equal to corresponding state variable, that is U of t. Then E naught of t, output voltage corresponding, it is measured across voltage. This is measured across capacitor. The output voltage is measured across capacitor. That is Y of t. Now write down the network equation applying basics law, Ohm's law and Kirchhoff's law. So this is a series network. We can apply Kirchhoff's voltage law. The algebraic sum of potential rise is equal to algebraic sum of potential drop in a closed circuit. Okay. So now write down EI of t is equal to voltage drop across resistor plus voltage drop across inductor. So L into di of t by dt plus voltage drop across capacitor 1 by C integral of I of t into dt. Again, so E naught of t output is measured across capacitor. It is nothing but voltage drop across capacitor. So that is 1 by C integral of I of t into dt. Say this is equation number 1. So this is equation number 2. From equation 1, keep L into di of t by dt one side. Bring all other term into other side. So L into di of t by dt. Bring all other term into other side. Minus I of t into R minus 1 by C integral of I of t into dt plus dI of t. Now again divide L for whole equation. So di of t by dt is equal to minus R by L I of t minus 1 by L C integral of I of t into dt plus 1 by L dI of t. Now replace this variable by physical variable by state variables. We have taken current through the inductor as a one state variable. So I of t is equal to x1. Now replace. So that is dx by dt, that is x1 dot first order derivative minus r by l. I of t is x1 state variable, we have switched corresponding to the inductor, minus 1 by l, that is 1 by c integral of I of t nothing but voltage across capacitor. This is an x2 of t plus 1 by l. I of t integral c of t, that is input. Okay. Then, so this is equation number 3 from equation 2. So dc of t is equal to 1 by c integral of I of t into dt. Now differentiate with respect to time t on both sides. So dc of t by dt is equal to, so the taking differentiation, so integration get cancelled. 1 by c I of t. So this dc of t we take a state variable x2, so x2 dot. So this can be replaced with x2 dot 1 by c I of t is x1. So this is equation number 4. Now write equation number 3 and 4 in matrix form. 3 and 4 in matrix form. Matrix form. So x1 dot of t, x2 dot of t, this state vector. Now equation 3, this is equation 3, x1 coefficient minus r by l, x2 coefficient minus 1 by l. From equation 4, only x1 is there, 1 by c, there is no x2 term, so x2 coefficient 0. From equation 3, so 1 by l, u of input. From equation 2, there is no input term, 0. So this is a state equation. This is a state equation. Then output equation, that is output is measured across capacitor. So I of t, so that is voltage across capacitor is x2. So there is no x1 term because y of t is equal to dc is nothing but x2. There is no x1, so put x1 coefficient 0. So x2 is there, so that coefficient is 1. x1 of t, x2 of t. So generally the transmission matrix D was 0. So this is an output equation. So the state equation, output equation gives state-based model of the given electrical network.